This chapter looks at ductile deformation processes. This is something that can happen to all three types of rock. Of course, we're talking about sedimentary, igneous, and metamorphic, not classic punk and hard. Now, to start out, we want to ask a couple fundamental questions. How can something like strong rock be permanently bent into a tight fold? This can happen on tiny scale and on huge mountain scales. We see whole mountainsides folded. How can this happen? How can something solid like ice distort while still remaining solid? This can happen much, much faster. We can see this happening. We can see glaciers, and we can see that they're flowing and bending. On a small scale, you can have a chunk of ice, a block of ice, or an icicle that you bring in from outdoors, put it in your freezer, braced up on top of something, tie a little string like a piece of floss around it, and dangle something heavy from that string. Keep this in your freezer, and that string will actually go down through the ice, and your object will drop down, pulling the string all the way through, but the ice will stay solid. It'll still be that icicle or block of ice or whatever. How can this happen? How can nice normal students turn into raving lunatics? Pretty much the exact same cause. Pressure and stress. These are tremendous. They can do crazy things. So this chapter is looking at ductile deformation. And so what are the mechanisms or parameters that affect ductile deformation? Well, there are three mechanisms, one of which you've already seen. There's cataclastic flow, there's diffusional mass transfer, and there's crystal plasticity. So those are the mechanisms. The parameters that control deformation are temperature, stress, strain rate, grain size, composition, and fluid content. Now, temperature is probably the easiest one to understand. If you have a really cold temperature, like the inside of your freezer, and you have something plastic in there, it doesn't bend very easily. In fact, you'll probably break it if you try bending it. If you let it warm up to room temperature, the plastic may or may not be a little bit flexible. Run it under hot tap water from your faucet for a while, and it'll get really flexible. Throw it in your oven, and it'll probably be so flexible it'll drip down all over the bottom of your oven, and you'll wish you hadn't listened to me and hadn't tried that. Now, stress. Stress affects deformation. It's generally the cause of the deformation. So the greater the stress, the greater the deformation. Strain rate. So, we're deforming something, but how fast is going to determine whether it's plastic or brittle. It's like if you have a really big shelf and you gently set a heavy weight on the middle of the shelf, that shelf is going to flex. You're causing plastic deformation in your shelf. On the other hand, if you hold that heavy weight a little ways above your shelf and then just drop it so that it hits it abruptly, you're going to break your shelf. You're going to have brittle deformation. So strain rate is really important. Grain size affects the deformation that happens in your rock. If you've got very large grain sizes, you're more likely to have certain kinds of deformation than if you have very small grain size. Composition. This, of course, matters because different composition means you have different minerals, different physical attributes, different melting temperatures, different strengths. And fluid content. Fluid content is important because rocks interact with the fluid. More fluid content means you can deform the rock more easily, similarly to how the higher fluid content resulting in higher pore pressure allowed for easier fracturing. We can also have easier plastic deformation. Ductile deformation, plastic deformation, same type of deformation, different terminology. Now, temperature. As we talked about different compositions, different minerals, each have different melting temperatures, but also different temperatures at which they act ductilely, where they behave plastically, and where they start bending without melting. The closer they are to their melting temperature, the more easily they will bend and flow. Again, without melting, because it's as they approach their melting temperature. Now, to talk about this, we would want something that was normalized. So if something like quartz that has a lower melting temperature is 5 degrees short of melting, and something with a very high melting temperature like olivine is 5 degrees short of melting, which one's closer? Well, you say, well, neither one. They're both 5 degrees away. But percentage-wise, the quartz is closer because it doesn't take as high of a temperature. And so, if we're normalizing, we're worrying about not what degree it is or how many degrees away from melting, but how close as a ratio, as a percentage. And so we use homologous temperature, or T sub H. T sub H, homologous temperature, is the current temperature of the rock, or the mineral, divided by the melting temperature for that mineral. Now, both the temperature and melting temperature have to be in absolute temperature, in Kelvin. Because they're both in Kelvin, this makes the homologous temperature unitless. The units cancel out. You just have a number somewhere between 0 and 1. It's always going to be between 0 and 1, because 0 would imply that you actually have something at absolute 0, and if you pull that off, quit taking this class and go claim your Nobel Prize, because we can't do that yet. On the other hand, if you have a value of 1, it means you melted your object. So it's no longer solid, it's melted. So it's always going to be between 0 and 1.